The Earth, a dynamic planet where fire and rock collided with life, has a history shaped by numerous volcanic activities. These fiery forces sculpted the landscapes and ecosystems long before human existence. Massive lava flows and catastrophic supervolcanoes forged a path that would dictate the future of life on our planet. In the distant past, when the Earth was still young and restless, the frequent volcanic eruptions were among the dominant natural phenomena, paving the way for countless geological transformations. Volcanoes have been some of the Earth's most powerful architects. They molded the planet's surface, forming vast mountain ranges, creating fertile lands and even forging new landmasses. The interaction between molten rock and the biosphere resulted in changes that had lasting impacts. Lava flowing down from an eruption would annihilate everything in its path. But once it cooled and solidified, it created fertile soils that could support vibrant ecosystems. Such duality made volcanoes both destroyers and creators, playing a pivotal role in the cycle of life. Supervolcanoes pushed these formations to the extreme. Their eruptions could blanket entire regions in ash, leading to dramatic shifts in climate and biomes. These events could drastically reduce temperatures, causing volcanic winters that brought about mass extinctions. However, this very ash enriched the soil, leading to bursts of new life in the aftermath. One such example is the infamous Yellowstone caldera, a supervolcano whose eruptions altered vast swathes of North America, affecting climates and ecosystems far beyond its immediate vicinity. The symbiosis between volcanoes and life is a story of resilience and rebirth. In prehistoric times, volcanic islands served as cradles of evolution. Isolated from the mainland, these islands became hotbeds of unique biodiversity. Species had to adapt to the harsh, ever-changing environments created by frequent eruptions, leading to innovative ways of survival and evolution. Galapagos Islands, known for their unique species, owe their existence to underwater volcanic activity that pushed the land above sea level, creating habitats for distinctive flora and fauna. Today, scientists study past volcanic activities to understand their influence on Earth's geological and biological history. By examining layers of volcanic ash and rocks, they unravel the secrets of our dynamic planet. Learning how ancient eruptions impacted past climates and species, we gain valuable insights into current and future volcanic threats. These historical narratives remind us of the raw power of our planet and the delicate balance between destruction and creation. Through these tales of fire and rock, we are better equipped to appreciate the ever-evolving saga of life on Earth. Volcanoes have been a force of nature since the Earth's inception, some 4 billion years ago. In the planet's infancy, Earth was a seething molten mass of magma, a fiery globe with no solid ground to speak of. This tumultuous beginning set the stage for volcanic eruptions to play a pivotal role in shaping our planet's surface. As the molten rock began to cool, it solidified to form the Earth's first crust, triggering a ceaseless cycle of eruptions that would gradually construct vast landmasses. These early volcanic eruptions were monumental, spewing out not just lava but also ash and gases that covered the young planet. Over time, the cooled lava gave rise to Earth's primordial continents. This process was neither swift nor serene. It was marked by relentless forces of destruction and creation. Volcanic activity, driven by the shifting tectonic plates beneath the Earth's crust, continued to mold the landscape, producing mountains, valleys, and even islands seemingly out of nothing. The sheer power of these eruptions was awe-inspiring, leaving a dramatic impact on the Earth's topography. But volcanoes did more than just shape the land. They created the bedrock of life itself. The material ejected from deep within the Earth was rich in minerals, laying down layers of fertile ground upon which life could flourish. These minerals included essential nutrients such as potassium, phosphorus, and magnesium, which are vital for plant growth. As rain broke down volcanic rocks and mixed with soil, the resulting nutrients created some of the most fertile environments on the planet. This fertile land acted as a cradle for the emergence of diverse ecosystems, allowing life to grab hold and proliferate. Volcanoes also contributed to Earth's atmosphere, releasing vast amounts of water vapor, carbon dioxide, and other gases. These gases played a crucial role in forming the planet's early atmosphere and hydrosphere, setting the stage for weather patterns and climates conducive to life. Volcanic activity helped to populate the oceans and rivers with vital elements, creating a dynamic environment where life could continue to adapt and evolve. The interplay between volcanic activity and the atmosphere established conditions suitable for the rise of complex organisms. Over billions of years, volcanoes have remained both a creator and a destroyer in the Earth's natural history. Even today, they continue to shape our planet, reminding us of their ancient legacy. Their significance extends beyond geological formations. They are the unsung heroes of our biological heritage. The violent eruptions of the past are responsible for the rich, life-sustaining environments we benefit from today. In understanding volcanoes, we gain insight into the primal forces that have brought forth and nurtured the life we see around us. The story of our vibrant planet begins with the fiery wrath of molten lava. As lava erupted and flowed across the landscape, it eventually began to cool and harden. This cooling process set the stage for a transformation that would change the fate of our world. Over time, the cooled lava cracked, weathered, and broke down, transforming into rich volcanic soil. These soils were laden with essential minerals and nutrients, forming the fertile foundation necessary for life to flourish. Given millions of years, this nutrient-rich volcanic soil became a cradle for early ecosystems. The soil's wealth of minerals such as potassium and phosphorus provided the essential building blocks for plant life. The introduction of water to these minerals triggered a series of chemical reactions, enabling the development of primitive plant species. These early plants played an essential role, not just as the first life forms, but as the architects of their environment, contributing to the organic matter in the soil and creating a suitable habitat for other life forms. Water, the elixir of life, began to carve its path through these volcanic minerals, blending them with organic matter. Streams and rivers carried these vital ingredients to different parts of the landscape, fostering life in various regions. The interplay between volcanic minerals, water, and organic matter was crucial in establishing nutrient cycles and supporting plant growth. These combined elements formed a synergy that made the soil even more fertile, enabling diverse plant species to take root and thrive. As plant life flourished, so did the ecosystems they supported. These thriving plant communities offered sustenance and shelter for animal species. Early insects, invertebrates, and eventually vertebrates relied on these plants for nutrition and habitat. The relationships between plants and animals became intricate and symbiotic, paving the way for more complex interactions and dependencies. This burgeoning complexity was a precursor to the advanced ecosystems we recognize today. Over the millennia, the ongoing process of decomposition and regeneration further enriched the volcanic soil, creating a continuous cycle of growth and renewal. Decomposing plant matter returned nutrients to the soil, ensuring its perpetual richness. These nutrient-packed soils, originating from once molten lava, literally formed the bedrock of life. This cycle of decay and renewal not only sustained existing life forms but also allowed for the evolution and emergence of new species, contributing to the planet's biodiversity. Ultimately, the once barren volcanic landscape metamorphosed into a thriving web of life. The combination of volcanic minerals, water, and organic matter forged a life-sustaining environment. This synergy laid the groundwork for the evolution of complex life forms, from simple plants to advanced ecosystems teeming with diverse flora and fauna. Our planet's rich and varied ecosystems owe their existence to the dynamic processes that began with cooling lava and culminated in the grandeur of life as we know it. Volcanic eruptions have been the unsung architects of Earth's diverse habitats. When molten lava meets the ocean's cool embrace, it forms new land masses, while ash clouds rejuvenate the soil. These dramatic events have not only reshaped the planet's surface but also played a crucial role in life's early development. The rich nutrients released during eruptions served as catalysts, nurturing primitive ecosystems and fostering life's emergence in a myriad of environments. The early Earth was a tumultuous landscape, marked by frequent and violent volcanic activity. These eruptions blanketed the land with mineral-rich ash and filled the atmosphere with essential gases. As lava solidified, it created new land that teemed with life-giving compounds. This primordial cocktail of elements, including sulfur, potassium, and phosphorus, provided the essential building blocks for nascent biological processes. This fertile ground allowed the first microorganisms to thrive, setting the stage for the complex web of life that would follow. In the oceans, volcanic activity had an equally profound impact. Hydrothermal vents, often found along mid-ocean ridges, expelled heated, mineral-laden water into the surrounding sea. These underwater geysers created localized oases of life, known as vent communities. Here, chemosynthetic bacteria harnessed the chemical energy in the vents' emissions, forming the base of a unique food web. This process demonstrated life's incredible adaptability, thriving in environments once thought too extreme to support it. As volcanic islands emerged from the sea, they brought a new dynamic to Earth's biosphere. Pioneer species such as lichens and mosses colonized the freshly formed rock, breaking it down over time into nutrient-rich soil. This slow but steady transformation created hospitable conditions for more complex plant and animal life. Island chains became laboratories of evolution, where isolated ecosystems fostered biodiversity and the emergence of unique species. The cycle of eruption and colonization continually reshaped these habitats, promoting resilience and adaptation. On land, the ash and pumice from volcanic eruptions played a similar role in nurturing life. After the initial destruction, the fresh ash layers quickly began to decompose, releasing nutrients that rejuvenated the soil. Forests regrew, and new plant species adapted to the mineral-rich environment, providing food and shelter for diverse animal populations. This process of regrowth and adaptation was a testament to nature's resilience, where life repeatedly sprang from the ashes, more vibrant and varied than before. In conclusion, volcanic eruptions were pivotal in creating and sustaining diverse habitats on early Earth. By distributing essential nutrients across both land and sea, they set the stage for life's evolution in myriad forms. These cataclysmic events, far from being merely destructive, were instrumental in shaping the rich tapestry of life that flourishes today. Without the dynamic and nurturing influence of volcanic activity, the Earth's biosphere would lack much of its complexity and beauty. Volcanic activity has been a fundamental force shaping life on Earth. While its contributions to creating fertile lands and enabling life are well documented, the destructive power of supervolcanoes cannot be overlooked. These colossal geological forces have occasionally served as nature's harbinger of doom, causing mass extinctions and altering the course of evolution. One of the most dramatic examples of such an event is the eruption of the Siberian Traps, which occurred around 250 million years ago. The Siberian Traps represent one of the largest volcanic events to have ever occurred on our planet. This cataclysmic eruption unleashed vast amounts of lava, covering an area larger than the size of modern-day Europe. The sheer scale of this event is difficult to comprehend. Towering fountains of molten rock reshaped the land almost overnight, forming a vast plateau of hardened basalt. This event pumped immense quantities of greenhouse gases such as carbon dioxide and methane into the atmosphere, drastically altering the Earth's climate. The climatic consequences of the Siberian Traps were dire. The sudden surge in greenhouse gases led to a sharp increase in global temperatures, triggering what is known as the Permian-Triassic extinction event. This period saw the elimination of about 96% of marine species and 70% of terrestrial vertebrate species. The Earth's oceans became highly acidic, causing severe disruptions to marine life. Land ecosystems were equally devastated. Forested areas turned into barren landscapes, and the diversity of life forms plummeted. Beyond its immediate destruction, the Siberian Traps eruption had long-term ecological impacts. The high levels of sulfur dioxide released into the atmosphere led to acid rain, which further damaged plant and animal life. This sulfuric haze blocked sunlight, creating a nuclear winter scenario that cooled the planet temporarily. The fluctuation between intense heat and sudden cooling caused ecological stress, making it difficult for surviving species to adapt. This set the stage for new evolutionary paths, ultimately allowing for the rise of new species. Despite its apocalyptic consequences, the Siberian Traps legacy is a testament to the dual nature of volcanic activity. While it caused one of the most significant mass extinctions, it also paved the way for new forms of life to emerge. The destruction of dominant species created ecological niches that newcomers could exploit, leading to a gradual recovery and diversification of life in the ensuing millions of years. This cataclysm exemplifies the cyclical nature of Earth's history, where colossal destruction often precedes rebirth and renewal. In today's context, studying events like the Siberian Traps is crucial for understanding the potential impacts of modern environmental changes. By examining these ancient cataclysms, scientists can gain insights into the mechanisms driving climate change and mass extinction. This knowledge is vital for developing strategies to mitigate the effects of contemporary ecological challenges. The story of the Siberian Traps is a stark reminder of nature's unpredictable power and the delicate balance that sustains life on Earth. The Earth has witnessed many natural catastrophes throughout its history, but few compare to the scale and devastation of the Permian-Triassic extinction event. This immense volcanic event was more than just an eruption. It was a global cataclysm that reshaped life on Earth. Over an area of more than 2 million square kilometers, volcanic activity unleashed colossal amounts of lava, gases, and ash into the atmosphere, fundamentally altering the planet's climate and ecosystems. As the volcanic eruptions raged, they released toxic gases like sulfur dioxide into the atmosphere. This noxious gas filled the air, causing widespread acid rain that devastated plant life and contaminated water sources. The skies darkened as ash and sulfur dioxide blocked out the sun, plunging the Earth into a period of chilling darkness. This lack of sunlight disrupted photosynthesis, causing plant life to falter and leading to a catastrophic collapse in the food chain. With the sun's rays blocked from reaching the Earth's surface, temperatures plummeted globally. The rapid cooling had a devastating impact on both marine and terrestrial environments. Habitats that had flourished for millions of years were suddenly inhospitable, and species unprepared for the dramatic change in climate couldn't survive. Coral reefs, which were crucial marine ecosystems, bleached and crumbled while life on land faced its own dire consequences. Marine species were hit particularly hard. Nearly 90% of all marine species were wiped out, making this event the single largest extinction of ocean life in Earth's history. Fish, mollusks, and other sea creatures that once thrived in the warm, nutrient-rich waters found themselves struggling to endure the frigid temperatures and acidic conditions. Surviving species were forced to adapt or migrate to find suitable habitats, further stressing the already fragile ecosystems. On land, the effects were equally catastrophic. About 70% of terrestrial species were lost during this period. Ancient forests died off, replaced by barren, lifeless landscapes. With a significant decline in plant life, herbivores found it increasingly difficult to find food, leading to their starvation and further predating carnivore species' sudden decline. The ecosystems that supported diverse life forms were now shadows of their former selves, teeming with far fewer species and drastically altered climates. In the aftermath of the Permian-Triassic extinction event, the Earth was forever changed. The extinction paved the way for the rise of new species and the eventual dominance of dinosaurs. But the planet would take millions of years to recover fully. This event serves as a grim reminder of the delicate balance within our ecosystems and the potential for natural phenomena to disrupt life on a global scale, leaving an indelible mark on the history of our planet. The Siberian Traps eruption stands as one of the most cataclysmic events in Earth's history, playing a pivotal role in driving the Permian-Triassic extinction. This colossal volcanic event unleashed an almost unimaginable volume of lava, spanning over a vast region in what is now Russia. The ferocity and scale of the eruption were such that it fundamentally altered the global climate system, setting the stage for a mass extinction event unparalleled in its devastation. The sheer magnitude of the volcanic activity released a deluge of greenhouse gases, including carbon dioxide and methane, into the atmosphere. These gases rapidly transformed the Earth's climate, creating a runaway greenhouse effect. Temperatures soared globally, creating inhospitable conditions for many forms of life. Dense clouds of ash and sulfur dioxide not only blocked sunlight, but also caused acid rain, acidifying the oceans and soil. The combined atmospheric impacts created a hostile environment on both land and sea. On land, ecosystems collapsed as temperature extremes, toxic gases, and acid rain wreaked havoc. Forests withered and died, unable to survive the rapid climatic shifts. Herbivorous animals lost their food sources, leading to a catastrophic chain reaction through the food web. Apex predators faced mass starvation as their prey dwindled, and terrestrial biodiversity plummeted. Microbial life, more adaptable to extreme conditions, started to dominate, altering ecological balances and leading to further disruptions. The oceans fared no better. The acid rain from the eruption caused ocean acidification, decimating marine life. Coral reefs, the marine equivalent of rainforests, experienced widespread die-offs, eliminating crucial habitats for countless species. Furthermore, the warming waters triggered the release of methane hydrates from ocean floors, exacerbating global warming. Anoxic conditions spread across vast swaths of the ocean, suffocating marine fauna. These dead zones saw mass extinction of marine organisms, including essential plankton populations that formed the base of the marine food web. In the aftermath of this prolonged period of devastation, the Permian-Triassic extinction event left the Earth eerily quiet and genetically impoverished. The once vibrant ecosystems, teeming with diverse life, were reduced to shadows of their former glory. It took millions of years for life to recover, with new species gradually emerging to repopulate the planet. The Siberian Traps eruption serves as a stark reminder of the fragility and resilience of life on Earth, highlighting the profound impacts volcanic activity can have on global biodiversity. In modern times, studying this ancient eruption provides crucial insights into the consequences of dramatic climate shifts and the resilience of life. Understanding these ancient events helps scientists predict potential future outcomes in our rapidly changing world. As we face our own climate challenges and environmental crises, the lessons of the Siberian Traps eruption underscore the importance of proactive and informed efforts to preserve the biodiversity and ecological stability we still have. Volcanic lava flows have dramatically reshaped our planet's landscape, leaving an indelible mark on prehistoric ecosystems. One of the most significant examples is the Deccan Traps in India, which erupted approximately 66 million years ago. These continuous lava flows covered vast areas, transforming the terrain and influencing the flora and fauna that inhabited the region. The sheer volume of lava emitted from the Deccan Traps was astonishing. Stretching over 500,000 square kilometers, the flows spewed cumulatively over 1 million cubic kilometers of basalt. This volcanic activity created an inhospitable environment for many species, causing a significant die-off, but also laying the foundation for new life forms to adapt and evolve. As the land cooled, new habitats emerged, radically changing the ecological balance. As lava flows solidified, they formed magnificent plateaus and mountain ranges that altered local climates. The newly formed topography influenced wind patterns and precipitation, resulting in the creation of microclimates. These microclimates became isolated pockets where certain species could thrive, while others faced new challenges. Over time, life adapted to these new conditions, leading to unique evolutionary paths and biodiversity. The intense heat from the lava flows incinerated nearby vegetation and dramatically altered soil composition. Rich, fertile volcanic soils eventually replaced the scorched earth, creating lush landscapes conducive to plant growth. These new plant species provided sustenance for herbivores, creating a domino effect up the food chain. Predators and prey adapted in tandem, evolving new strategies for survival in their altered world. Beyond immediate ecological impacts, these lava flows played a role in global events such as the Cretaceous-Paleogene (KPG) extinction. The volcanic eruptions released massive amounts of greenhouse gases like carbon dioxide and sulfur dioxide into the atmosphere. This contributed to drastic climate changes, resulting in global cooling and acid rain. The shift in climate stressed ecosystems worldwide, leading to widespread extinction events, including the demise of non-avian dinosaurs. Interestingly, while many species perished, some managed to survive and even flourish in the changed environment. The hardship imposed by the volcanic activity acted as a catalyst for evolutionary innovation, prompting species to develop new physical traits and behaviors to cope with their surroundings. Mammals, in particular, began to diversify, setting the stage for the rise of mammals in the post-dinosaur era. In conclusion, the volcanic lava flows of the Deccan Traps significantly reshaped prehistoric ecosystems by altering landscapes, creating new habitats, and impacting global climates. While these cataclysmic events posed enormous challenges for existing life forms, they also spurred evolutionary progress, ultimately increasing biodiversity. The reverberations of these ancient volcanic activities are evident in the intricate web of life we see today. The Deccan Traps eruptions, occurring around 66 million years ago, represent one of the most extensive volcanic events in Earth's history. These eruptions spanned thousands of years, covering vast regions with thick layers of lava. While their connection to the mass extinction that wiped out the dinosaurs is still under debate, their impact on the planet's climate and ecosystems is undeniable. The immediate effects of these eruptions were catastrophic. As lava flowed relentlessly, it smothered ecosystems, leaving once bustling habitats barren and lifeless. Plants, unable to survive the molten onslaught, died en masse, while animal species faced the dual threat of habitat loss and toxic volcanic gases. The scale of destruction was immense, with entire regions becoming inhospitable almost overnight. Beyond the immediate devastation, the Deccan Traps had profound long-term impacts on Earth's climate. The eruptions released vast amounts of sulfur dioxide and carbon dioxide into the atmosphere. Sulfur dioxide formed aerosols that reflected sunlight, leading to a dramatic drop in global temperatures, a phenomenon known as volcanic winter. Consequently, surviving species endured colder climates and shortened growing seasons, which further strained biodiversity. Conversely, the buildup of carbon dioxide over time contributed to a greenhouse effect, eventually causing global temperatures to rise. This dual climatic shift, from volcanic winter to global warming, created severe environmental stress. Species that had weathered the initial cold faced new challenges as their habitats once again transformed, this time becoming warmer and potentially more arid. Marine ecosystems were not spared from the turmoil. The oceans absorbed significant amounts of volcanic gases, resulting in acidification. This chemical change threatened marine life, particularly organisms with calcium carbonate shells, such as plankton, corals, and shellfish. The collapse of these foundational species had cascading effects throughout the marine food web, further contributing to the crisis faced by Earth's biosphere. While it's compelling to link the Deccan Traps eruptions directly to the mass extinction of dinosaurs, the debate remains open among scientists. Some research suggests that the timing of the eruptions aligns too closely with the extinction for it to be mere coincidence, while other studies point to the Chicxulub asteroid impact as the primary extinction driver. However, it's plausible that the combination of volcanic activity and asteroid impact could have been a one-two punch, creating insurmountable conditions for the dinosaurs and many other species. What is clear, however, is that the Deccan Traps significantly altered Earth's climate and ecosystems, causing widespread and prolonged effects. This period of intense volcanic activity serves as a powerful reminder of the fragile balance that sustains life on our planet, and the dramatic changes that can occur when this balance is disrupted. Understanding these past events helps scientists predict and prepare for potential future climate threats, ensuring the continued survival of our planet's diverse life forms. Volcanic eruptions are often seen as devastating forces of nature, capable of eradicating entire ecosystems in a matter of moments. Towering plumes of ash darken the sky. Rivers of molten lava incinerate all in their path, and landscapes are reshaped in an instant. Yet within this apparent chaos lies the potential for a profound rebirth. The very destruction that wipes the slate clean also sets the stage for new beginnings and the emergence of life in its most vibrant forms. Once the lava cools and the ash settles, a remarkable transformation begins. Volcanic soils formed from the weathering of ash and rock are renowned for their fertility. Rich in essential minerals like phosphorus, potassium, and magnesium, these soils provide a nutrient-dense foundation for plant growth. Over time, as rain and wind break down volcanic materials, these elements become more accessible, fostering an environment ripe for colonization by flora and fauna. The renewal of life in these areas follows a fascinating trajectory. Hardy pioneer species, such as lichens and mosses, are the first to take root. These organisms are adept at breaking down the rocky substrate, gradually creating a more hospitable environment. Their decomposition adds organic matter to the volcanic soil, further enhancing its fertility. This sets the stage for more complex plant communities to establish themselves, each successive generation building upon the foundations laid by its predecessors. As vegetation takes hold, it forms a protective cover that anchors the soil and prevents erosion, allowing for the gradual development of a more stable ecosystem. Shrubs and trees follow, creating habitats for a myriad of animal species. Birds, insects, and mammals begin to repopulate the area, drawn by the growing abundance of food and shelter. The once barren landscape pulses with life, a testament to nature's resilience and adaptability. The cycle of destruction and rebirth, brought about by volcanic activity, also drives evolution in fascinating ways. Species that are able to adapt to the unique conditions of volcanic terrains often thrive, developing specialized traits that enable them to exploit new niches. This can lead to increased biodiversity and the emergence of entirely new species over time. The regenerative process witnessed in volcanic regions underscores the incredible capacity for renewal that defines our natural world. In this context, volcanic eruptions are both an end and a beginning. They remind us of the delicate balance between destruction and creation, and the inherent potential for life to rise anew from the ashes. As ecosystems evolve and recover, the scars left by volcanic events become the fertile grounds from which vibrant new life springs forth, illustrating that even out of the greatest devastation, hope and renewal are possible. In the aftermath of volcanic eruptions, the initial impression is often one of utter devastation. The landscape appears inescapably barren, coated in layers of ash and lava, and the air seems thick with the residue of turmoil. Yet hidden within this apparent wasteland lies the potential for a spectacular rebirth, driven by the remarkable processes that govern nature's inclination toward recovery. The nutrient-rich soils formed from volcanic ash and lava flows set the stage for this rapid revival. These soils, packed with minerals like potassium, phosphorus, and magnesium, provide an ideal breeding ground for all kinds of plant life. Within a surprisingly short period, pioneer species, those first brave plants that colonize disturbed lands, begin to emerge. Mosses and lichens are typically among the first to take root, their presence marking the beginning of a complex ecological succession. As these pioneer species prosper, they create conditions that allow other plants to germinate and grow. Ferns, grasses, and eventually shrubs take hold, each contributing organic matter to the soil as they live and die, enhancing its fertility and structure. This succession process attracts various animal species, such as insects, birds, and small mammals, drawn by the availability of new habitats and food sources. Furthermore, volcanic landscapes often become hotspots of biodiversity. The harsh conditions favor species that are highly adaptable and resilient, leading to a diverse array of flora and fauna that might not have thrived in more stable environments. For instance, flowering plants unique to volcanic regions often emerge, their seeds spread by wind and animals, quickly transforming the scorched earth into a vibrant mosaic of life. Water plays a crucial role in this regeneration as well. Rainfall washes nutrients deeper into the soil, ensuring that even the smallest plants get the sustenance they need to grow. Rivers and streams, reshaped by the volcanic activity, carve new pathways through the terrain, creating wetlands and aquatic habitats that further enhance biodiversity. These bodies of water become vital lifelines for both terrestrial and aquatic creatures. Human intervention occasionally accelerates this natural recovery process. Reforestation efforts and the introduction of native species can jumpstart the rejuvenation of ecosystems, especially in areas where natural recovery might be slower due to extreme conditions. However, it is often observed that nature, left to its own devices, is remarkably efficient at healing itself. Ultimately, the recovery of ecosystems post-volcanic events is a testament to the resilience of nature. From the first shoots of green pushing through the ash to the richly diverse ecosystems that follow, these transformations remind us of the inherent beauty and strength of the natural world. Despite the initial destruction, the landscape eventually blossoms, illustrating that the cycle of life is unyielding and ever-renewing. In more recent history, volcanic activity continues to play a significant role in shaping landscapes and ecosystems. The eruption of Mount St. Helens in 1980 was a powerful reminder of the Earth's volcanic might, creating a scene of devastation that seemed almost apocalyptic. Ash spewed into the sky, covering miles around in a thick, suffocating blanket, and the mountain itself was transformed, its peak blown away in a fiery explosion. In the immediate aftermath, the area around Mount St. Helens resembled a lunar landscape, barren and gray. Trees were uprooted, rivers choked with debris, and wildlife seemingly vanished. The sheer force of the eruption had leveled entire forests and created a wasteland where life struggled to find a foothold. Yet even in this desolate scene, the resilience of nature began to show itself. Tiny seeds carried by the wind settled into the ash-laden soil, and slowly, the first signs of recovery began to appear. Within years, the landscape started to heal. Pioneer species like lupines and fireweed spearheaded this resurgence, their vibrant colors a stark contrast against the monochrome backdrop. These hardy plants laid the groundwork for other species, enriching the soil and creating habitats for insects and birds. Prairie lupine seeds found purchase in the nutrient-rich but desolate soil, their growth paving the way for other flora and fauna. Life's return to Mount St. Helens was not limited to plants. Animals attracted by the burgeoning plant life cautiously made their way back. Elk and deer, driven from their habitats during the eruption, returned in search of food and shelter. Small mammals like pocket gophers and birds such as the northern flicker began to repopulate the area, bringing movement and sound back to the once silent wilderness. The rebirth of this ecosystem illustrated nature's capacity for recovery and adaptation. Today, the recovery of Mount St. Helens stands as a testament to the resilience of life. Forests of young trees now cover what were once bare slopes, while streams cleared of ash and debris run clear and full of fish. Scientists study the area as a living laboratory, learning valuable lessons about ecological succession, species adaptation, and the intricate web of life that binds even the most devastated landscapes together. They observe the flora and fauna interact in a delicate dance, rebuilding the environment one day at a time. The story of Mount St. Helens serves as a powerful reminder of both the destructive power and the incredible healing ability of nature. As life reclaims the landscape continues to evolve, bearing witness to the dynamic processes that shape our planet. From the ashes of devastation has sprung a vibrant tapestry of life, demonstrating that even in the wake of chaos, life persists and thrives. Mount St. Helens is a symbol of hope, showing that recovery is always possible no matter how grave the destruction. Studying modern volcanic eruptions provides valuable insight into the impact these events have on ecosystems. By examining contemporary data, researchers can make informed inferences about how ancient ecosystems may have responded to similar volcanic activities. Volcanoes, often seen as destructive forces, offer a dual nature. They not only cause chaos but also play a crucial role in shaping the world as we know it. When a volcano erupts, it emits a vast array of materials including ash, gases, and lava. These materials can lead to immediate changes, such as the destruction of habitats and alteration of landscapes. However, beneath this initial devastation lies the potential for renewal. The ash and lava deposited by eruptions can create fertile soils over time, providing a new foundation for plant growth and, consequently, the return of wildlife. This regenerative aspect demonstrates the balance between destruction and creation in volcanic activity. Across the globe, ecosystems have shown a remarkable ability to adapt to volcanic disturbances. For example, certain plant species have evolved to thrive in nutrient-rich volcanic soils, and some animals have developed behaviors to escape or cope with eruptions. Observing these adaptations provides scientists with a living laboratory to understand the mechanisms of evolution. It highlights the importance of environmental pressures in shaping genetic diversity and resilience. Volcanoes also play a pivotal role in the biogeochemical cycles of the Earth. The release of gases such as carbon dioxide and sulfur dioxide during eruptions influences the climate and atmospheric composition. These changes can have profound effects on global temperatures and weather patterns. Historical eruptions have been linked to significant climate events, such as the cooling periods following major eruptions like Mount Tambora in 1815. By studying these patterns, researchers can better predict future climatic shifts resulting from volcanic activity. Moreover, examining volcanic islands such as the Galapagos provides unique insight into the process of colonization and biodiversification. These islands formed by volcanic activity offer a pristine environment where life can evolve in relative isolation. The unique flora and fauna of such islands illustrate the dynamic interplay between geological processes and biological evolution, acting as natural laboratories for evolutionary biology. While volcanoes are indeed agents of destruction, they also serve as catalysts for new beginnings and adaptive evolution. The study of modern and ancient eruptions helps scientists unravel the complex interactions between geological and biological processes. This knowledge not only enriches our understanding of the Earth's history, but also prepares us to navigate future environmental challenges. By embracing the dual nature of volcanoes, we gain a greater appreciation for their role in the story of life on our planet. Volcanoes have played a pivotal role in Earth's history, acting as both creators and destroyers. From the planet's formative years, volcanic activity has significantly influenced the climate, ignited mass extinctions, and redefined landscapes. Despite their destructive power, volcanoes also harbor the potential for creation, giving rise to new life forms and ecosystems in their wake. In the primordial years, Earth's surface was a molten canvas, constantly reshaped by violent eruptions. These eruptions released gases that helped form the atmosphere, setting the stage for the development of early life. The relentless volcanic activity laid the groundwork for diverse habitats, where primitive organisms began to thrive. Ancient landscapes bore witness to a continuous cycle of destruction and renewal, driven by the fiery breath of volcanoes. Mass extinctions punctuated Earth's history, often triggered by intense volcanic eruptions. These cataclysmic events caused rapid climate shifts, leading to widespread loss of life. Despite such devastation, these periods also paved the way for evolutionary bursts, allowing resilient species to adapt and overcome the challenges posed by a drastically altered environment. The rise and fall of life dictated by volcanic influence underscore the delicate balance that governs Earth's biosphere. Volcanoes have also played a crucial role in shaping modern ecosystems. Eruptions replenish the soil with rich minerals, fostering lush vegetation in regions previously barren. Islands born from underwater volcanic activity become cradles of unique biodiversity, hosting species found nowhere else on the planet. These new environments offer fresh opportunities for life to flourish and adapt in extraordinary ways. The legacy of volcanic activity is etched into the fabric of Earth's geological and biological history. From the strikingly red landscapes of Mars to the volcanic moons of Jupiter, the pervasive influence of volcanic activity extends beyond our home planet. As we continue to study these natural phenomena, we gain deeper insights into the intricate processes that have shaped not only Earth, but other worlds in our solar system. Today, scientists closely monitor volcanic activity to understand its impacts on climate and life. Advanced technology enables the prediction of eruptions and mitigation of their effects, showcasing our growing prowess in deciphering nature's signals. Despite the progress, volcanoes remain enigmatic, with much still to be discovered about their inner workings and long-term influences. As the sun sets on volcanic peaks, casting golden hues across rugged landscapes, we are reminded of the relentless power and beauty of these natural giants. While they may bring about moments of destruction, volcanoes also signal rebirth and renewal. In their shadows, life perseveres, adapting and evolving to face the challenges posed by an ever-changing world. The story of volcanic activity is a testament to nature's resilience, revealing a profound interconnectedness that shapes the history and future of life on Earth. In the annals of our planet's history, few events encapsulate the relentless dance between destruction and creation as vividly as the Great Firestorm. This colossal inferno, once thought to be a tale of myth and legend, continues to flicker in the collective memory of life on Earth. Sparks of this ancient blaze can still be found, echoing the precarious balance that sustains our world. The origins of the Great Firestorm lie in a time when the Earth was young, its crust yet unformed and the seas still steaming with primordial heat. Volcanic eruptions, fueled by the churning mantle below, spewed molten rock and ash into the atmosphere, igniting vast tracts of ancient flora. This inferno, raging unchecked, both heralded the end of an era and the beginning of another. From the ashes, the embers of new life took root. The firestorm's infernal dance was not a mere force of destruction. It was a crucible of transformation. Forests ignited in the blaze would give way to charcoal-rich soils. In the annals of our planet's history, few events encapsulate the relentless dance between destruction and creation as vividly as the Great Firestorm. This colossal inferno, once thought to be a tale of myth and legend, continues to flicker in the collective memory of life on Earth. Sparks of this ancient blaze can still be found, echoing the precarious balance that sustains our world. The origins of the Great Firestorm lie in a time when the Earth was young, its crust yet unformed and the seas still steaming with primordial heat. Volcanic eruptions, fueled by the churning mantle below, spewed molten rock and ash into the atmosphere, igniting vast tracts of ancient flora. This inferno, raging unchecked, both heralded the end of an era and the beginning of another. From the ashes, the embers of new life took root. The firestorm's infernal dance was not a mere force of destruction. It was a crucible of transformation. Forests ignited in the blaze would give way to charcoal-rich soils, fostering the growth of verdant new ecosystems. The cyclical process of burning and regrowth became a fundamental rhythm in nature's symphony. It showcased how resilience and adaptation are intricately woven into the fabric of life itself. As we look to our planet's past, the evidence of the Great Firestorm is etched in the geological record. Charcoal deposits, fossilized trees, and layers of soot speak of a time when fire reigned supreme. These remnants are a stark reminder of Earth's volatile nature and its capacity for regeneration. Life persisted, adapting to the ferocity of flames, evolving through cycles of destruction and rebirth. In contemporary times, the legacy of the Great Firestorm finds its reflection in the wildfires that continue to carve their mark upon our landscapes. Climate change and human intervention have exacerbated the intensity and frequency of these fires, pushing ecosystems to their limits. Yet, even as the flames consume, nature's tenacity shines through in the seeds that only germinate after a fire, or the species that thrive in post-burn environments. The story of the Great Firestorm is one of dichotomy. the delicate interplay between annihilation and creation, despair and hope. It is a testament to the inherent resilience of life and its ability to adapt and flourish amid the most brutal conditions. As we grapple with modern firestorms, both real and metaphorical, recalling this ancient dance reminds us of the timeless cycles that shape our world. In the end, the firestorm is more than a historical phenomenon. It is a symbol of Earth's enduring spirit. It whispers a message through the crackling flames, that from the heart of devastation springs the promise of renewal, and within the embers of destruction, life's potential forever burns.